Welcome, everyone. This is the first of two lectures on audio and health. So we've seen the use of accelerometers and in general gyroscope and magnetometer, so the IMU, for detection of activity as well as gait. Another and accelerometers are generally cheap. They are included in many devices and are often a good example of how really this can scale and offer information about our health that is unprecedented, it has a granularity that is unprecedented from a number of devices. The microphone is, however, another cheap sensor that can be used for the same purpose. It is embedded in many devices. Most of our watches, wearables, phones have it, as well as devices that we put around our house, such as home listening devices, home speakers. And this allows for anything that uses this sort of devices to scale to larger populations. Obviously, also, there's a time dimension as well, because these devices are listening to us continuously and all day around. And therefore, they offer an unprecedented view of our, of whatever they listen to. So our health could be one, our behavior. And this is a report from 2017 that shows that it's not just audio in general, but our voices can tell a lot about our health. So here in this report, they talk about vocal pattern that might signal post-traumatic stress disorder or even heart disease. With the idea, we'll talk about that in the second part of this two-part lectures, that the voice tract can be affected by the status of our cardiovascular health. For example, if our arteries and veins are hardened by a disease, then obviously perhaps the voice will sound different because those veins in the respiratory tract will be different. And there are other dependencies that can be highlighted. So what kind of things can sound be used to detect? We really, in this lecture, we'll see a lot about respiration, breathing. And so implications of that are the ones of wheezing, asthma, COPD, sleep apnea. But also there are things related to our voice that can lead to indication of mental health, depression and PTSD, post-traumatic stress disorder. Neurological diseases can also be affected, can also be diagnosed through sound and voice, Parkinson's, Alzheimer, even autism. And in the last part of this two-part lecture, we'll talk about cardiovascular, so coronary heart disease, atherosclerosis, are some of the examples of things that can be detected. So in this first image, I want to give you an idea, and obviously speaking about our voice, our sound, the sound coming out of our mouth, our respiratory tract. One of the things that has been tried is detecting wheezing, which is it's the normal breathing sound. And patients with COPD often have this sort of wheezing, and other respiratory diseases also do. So on the left, you see the description, well, the sound over time on the x-axis and amplitude of the sound of a normal breathing. And on the right, you see a wheezing episode. There is a energy, so a frequency diagram on the second row. And as you can see, the frequency distribution is quite different. You can already see it by eye. In the third diagram, you see a spectrogram, so time on the x-axis and frequency on the y-axis of the inspiration and expiration, so just one breathing sound. And if you compare it with the one you see on the right, where the wheezing episode happens during the inspiration, you see that it's quite remarkably different. And in the middle, there is a diagram, a couple of diagrams of a normal breathing sound and a wheezing sound. Now, if you look at the scale, you might not notice immediately because this graph is a little misleading. On the y-axis is not scaled in the same way. The one is much bigger than the other one. The intensity is much bigger on the right, so you get to 15. And you see around the frequency between perhaps 200 and 400, there is a big peak in the wheezing sound, which is not noticeable in the normal breathing sound. So all these things that you can imagine can be used by analyzing some signal processing in detecting wheezing automatically. And so there are a few papers that try to do this. I just picked one. Usual first thing, apply some band filtering to isolate the frequencies where we know just by experience that generally this wheezing sound can be represented. So you want to eliminate the low frequencies that might contain heart sounds, muscle sounds, and blood flow sounds. And so, and then the sound is divided in windows segments with 200 milliseconds overlap, and they are considering the power spectrum of this breathing sound. So we'll talk about this, and it's calculated using the FFT. So you essentially calculate the graph that I've just shown you. This is a frequency spectrum graph in the middle, and you calculate that. We can use hand windowing, as we've seen in lecture, to smoothen the sides of the windows as well. And this is done to highlight there. And in this graph, so let's start by looking at what happens here on the left. This is a graph we've seen 2 slides ago. The intensity is on the y-axis and the frequency on the x-axis. So you have a peak, which is the highest point of this window, this frequency graph, peak frequency. The median frequency, which essentially points out the 50%, so if you continue the considered area under this curve, and you point where the 50% distribution, half of the points on the side of the points on the other side, then you find that median frequency, and the bandwidth is taken between the 2 points, the 25% and the 75% area, indicating a bandwidth feature of this frequency spectrum distribution. Notice also on the x-axis those SI, and they essentially indicate the groups of where certain sounds of the wheezing might be highlighted. And in fact, these 3 particular groups are considered on the right as the 3 graphs. You have 3 graphs there that are essentially just considering the spectral representation and the frequency representation on those 3 little bits. So the first one is the one at the lower frequency, then the middle frequency, and then the top frequencies. And what you notice here is the difference between the wheezing group and the health group. So you already by eye see that in all the 3 graphs, there is a considerable difference in the distribution here. The wheezing group has more of that and less of perhaps another one. And so you by looking at how these are distributed, you see that essentially here in all of the 3 spectrum, there is more of one and less of the other one, essentially. So even just by looking in this different, you would just find that this is the case. They also looked at features calculated from either the time or the frequency domain, and the relevance in the recording, how important they were in detecting the wheezing. I won't talk about all of them, and some of them will come out also for other sound analysis that we looked at, but I will talk about a few of them, and some are relevant here and also later. So an envelope of the frequency spectrum is essentially a continuous line of the frequency as taken in a frequency plot. So you draw your frequency plot, perhaps you can frame it in various time domains, calculate the frequency plot, calculate the maximum frequency in that plot, and use that. And then out of those maximum frequencies, you create a plot like the one on the right that has all of these, all the maximum frequencies. And then you can also do some smoothing of this sometime. And we'll talk about the spectral analysis later, but essentially here you can just look at the black line, which is essentially an aggregator smoothing of the line that you see appearing in the graph that contains all the maximum frequencies per frame. Now, the energy of the signal is simple. So essentially, if you have a wave, this could be in time domain or in frequency domain. Let's say this is your purple line that you can see on the slide here. This is your signal. Well, if you project it all on the positive side of the axis, of the y-axis, then you can have the dark green signal, which is the power of your signal. It's all the positive there. And if you consider the energy is essentially the area under this curve that you have there. And it can be essentially it's an integral, but if you have a discrete signal, it will be a sum. The energy of the signal is something that is used quite a bit in audio, not that just in audio, to understand features. And obviously on this curve, on this energy of the signal, you can calculate all sorts of other measures like we have done on the, you can do this on the frequency as well as on the time domain. And on the frequency domain, looking at this image, you can also look at the peaks and the median peaks and all other things. Now, this is something less obvious I wanted to mention. We will probably use it very little, but some of the techniques you might find in some libraries contain it, and it's about linear prediction coefficients. And it's a technique that calculates the coefficient of a model that is able to predict the next sample of a sequence of audio samples. And so if you have a good model that is able to predict this sample, you will have some linear coefficients. And these coefficients are quite good at identify a bunch of features in your signal, for example, the pitch period. There might be some examples of this further on, but this is one of the LPCs are perhaps a thing that you will find in your libraries to be used. One thing that is very used, and you probably use it in your audio analysis, is the MEL frequency septral coefficient. And the idea here is that these are better than normal features over the definition of the spectrogram match our auditory wave of the perceived sound, the human perceived sound. I'll try to give you an intuition. So this is a spectrogram on the picture there, and you know we perceive sounds logarithmically, meaning that we perceive the difference between sounds at lower frequency more than the distance of sounds at higher frequency. And so if this is not mirrored by the spectrogram, then it doesn't mirror the reality of what we feel about the sound and how we feel it. And so this is a replication of a replica of what kind of transformation a MEL scale would apply. So if you have your sound on the x-axis on the Earth scale, then those frequencies, well, will not be transformed in a linear way in the MEL scale. So you see that the higher frequencies are scaled in a different way from the lower frequencies to mirror our ability of distinguishing different ranges of frequencies. And I think this is possibly the best intuition for you. If you have a spectrogram, this is a spectrogram on the right, not modified, so the ones we have seen until now, then once you have transformed your frequencies into MELS frequencies, then you will find that they would have highlighted certain frequencies and underlighted other frequencies. Here you can see the spacing between the frequencies and what they have highlighted. That means that it might be better to understand certain things about the audio. So these things turn out to work really well. How do you do this? Well, in general, you apply a DFT to generate the frequency from the time domain. You apply a log, and then you apply a discrete cosine transformation, which is a transformation which highlights the important part of the log DFT graph. That's all I'm going to say about this. And as a result, in this transformation, in the modeling, there will be a generation or a number of coefficients, in particular, something like 39 coefficients. And the first of these coefficients will be the ones that are generally used as features in audio modeling. I think that's all you need to know to use the libraries to understand MEL frequency structure coefficients. So let's try to see a bit more of the examples and what features have been used in the identification of this. So this is another paper that shows the light blue and the dark blue are the audio the audio in time domain of breathing in and breathing out, a person breathing in, breathing out in front of a phone. In fact, there's an example there. And then there is a ground truth from a chest strap of the breathing in and breathing out green, and then yellow, green, and then yellow, green. So how can we use this sort of information to understand? So first of all, signal processing. The signal is passed through filter so that some frequencies are isolated and some are cut out. In this case, they use an ACE or the Butterworth low-pass filter cutoff frequency of 1 kilohertz. And then, so the cutoff frequency is 1 kilohertz, but they also use a low-pass filter to highlight certain frequencies and smoothen the high frequencies, of course. They also try to eliminate coughs and yawning because they're only interested in pure breathing sounds. And this is done by considering the windowing, but also considering the max and median peak in the window, as we have seen in one of the first slides when we were considering wheezing. So those max and median frequency amplitude are used because in the case of cough and yawning, as you could imagine, the frequencies, a certain frequency will spike, and that's not something you have in normal breathing. And those signals are used to exclude samples that contain coughs and yawning. Then other time domain features are used to detect pauses in respiration, and you can, as highlighted here and in the picture, you can see it in the time domain that there are some minima here between the various respiration poses that can be isolated, and this can be used to do some segmentation, but also perhaps you may want to cut off the poses between the various frame segments. And so just to advance a bit more, there are ways in which you can identify snoring and non-snoring. So it's not just about breathing and the length of breathing, but also the snoring episodes. So I'll use this example to give you another set of features that I use for this. In the picture, you see a snoring episode highlighted as a piece of audio. And just there in the middle, there's a scaled up version where there's a part that contains the snoring, and then there's the silence, and then the breathing. So different amplitude for the snoring, different amplitude for the breathing, and the silence also. So you can see here already in the time domain, you have differences in amplitude. The features used here, and I will describe most of them, just in the next few slides are the number of zero crossing and energy of the signal, and the autocorrelation coefficient at 1 millisecond delay. We have already seen autocorrelation in one of the IMU lectures, but I will go back to it again. And the last one, which I'll not describe, is this concept on which I had one slide before, of this LPC linear coefficients that I've described before, that are this predictor model able to detect the next audio sample and the coefficients of that. And these are used also for this snoring or snoring detection. So this is kind of very, it's a good example of the type of features that I use generally in audio. So what is zero crossing? So if you consider a signal in the time domain, zero crossing is simply the measure in a window of time of how many times the signal goes up and down. So all those gray crosses are the zero crossing, whenever the signal crosses the zero on the y-axis. And this, as you can imagine, intuitively, this is correlated with the frequency. Why is it correlated with frequency? Well, the more you do this, the more likely it is that your frequency is high. And I hope this intuition is clear. We've also seen it in autocorrelation lecture 3. So the autocorrelation measures the correlation of the signal with itself at a different shift. So here, maximum correlation is when the signal completely overlaps. And so if you start maybe one window down and you put the signal on top, then it's correlated. And this is a minimum correlation of the signal. As you can see over there, I've tried to give you an example of the minimum correlation, the maximum correlation, but you can go back also to lecture 3 to see another example. So essentially, the signal shifted by a certain amount, and in two slides ago, it was mentioned that they use a correlation 1 millisecond delay. So given that step, we try to see if the signal is correlated, and that's a good measure of, it's a good feature for this, this example. Now, the energy spectrum is, sorry, I think I gave you 2 examples and not the third. The energy of the signal we have seen already is the representation of the area under the curve. And you can do a log of that to smoothen, to simplify. And so here in the picture, you would see, so this is essentially probably a distribution of how often in the data, how much each of the features represented in various types of data. The 3 types of data are data where the user was silent, unvoiced non-silent, so it's when the person is not making noise from voice, and when there is voice in the sound. And by looking at the distributions here, and this is for in the top is the zero crossing, then the energy log, autocorrelation coefficient features, and the first linear predictor, the LP coefficient. By just looking at this by eye, you can see that the 4 features somehow discriminate. So for example, the first feature, silence and voice non-silent, might overlap, but definitely the zero crossing of UV and S, the unvoiced non-silent, is different, has a different distribution. So here it might be, as we said, the zero crossing often talks in terms of frequency. So it might be that the frequency are different for those samples. It's quite diverse in terms of energy spectrum. And in terms of autocorrelation coefficient, also the red curve seems to be different. And for the last one, they seem to be a little bit more similar. I noticed that the energy spectrum is quite probably the best at distinguishing the three of them. But with the combination of the four of them, you will definitely be able to distinguish the various groups of signals with a machine learning framework. We've talked about voice, but mainly here at the moment, we were concentrating on voice in terms of wheezing and in terms of on sounds, but there are other aspects of the voice that concern the larynx and the vocal folds, and the fact that we produce no voiced or non-voiced sounds, or breathing sounds or voice sounds. It depends on how we use the folds, which are this little bit here in the middle of the larynx. That is essentially down here, and the vocal folds are something that vibrate in our respiratory tract. They actually vibrate at different frequencies for men and women. There are also additional sounds that are nasal, and they are concerning the cavity of our nose. I won't go much into detail about this, but just to say that when you look at voice from our voice tract, you will have certain characteristics that will be distinguishable. And in fact, this is a picture from Wikipedia of the frequency, a spectrogram really, frequencies of a person pronouncing I, U, and A. And you can see the differences in the highlighted main frequency, which is formant 1, formant 2, formant 1, formant 2, formant 1, formant 2, and you can look at where these formants are for the different frequencies, meaning that the vibrations of the vocal folds generate different frequencies for different voice sounds, which opens the door for automatic detection of this. We won't go into speech, although speech is very much an area of research in terms of health, understanding voice characteristics for example, how the voice changes for Parkinson. We won't do much today, but we'll do a bit more in the next lecture. For today, we will concentrate a little bit of on sounds for airflow, really. So it's really related with the tracheal, but not with the modulation of the folds for various vowels. And so if you consider a sound signal of airflow while we breathe as the one at the top, and if you calculate the energy, as we know how to do now, and calculate the log of that as well, and you compare that with the true flow of air measured with a mass, you can see that actually the log of energy represents very well the same shape. And so you can understand how this particular feature can be used to understand sounds and airflow sounds. So that's the kind of intuition I want to give you. We'll look a little bit more about this into the next in the context of diagnosis of sleep apnea, which I will describe in a minute, and also in combination with another sensor, an oxygen saturation sensor. So this is my cat that usually, I think I introduced him in one of the previous lectures, but he sleeps beautifully when I'm working. And well, sleep is very important for us, and sleep apnea is one of the diseases affecting sleep, and is affecting quite a large number of people. And it involved the cessation of flow of air lasting for 10 seconds, and it involves the drop in oxygen saturation in our blood of at least 4%. So these are the characteristics that a machine learning framework will be looking in the data to understand if a person is affected by sleep apnea. The person themselves might not realize, they might wake up with such episodes, but they might not realize they have it. And that's why it's important to detect this automatically. They might just think that they've been sleeping badly, but actually there's much more to it than just sleeping badly. I've highlighted here how the framework of detection of this works. So as we've seen in many of the other approaches, we process the sound signal with some windowing and bandpass filtering. There's some automatic segmentation happens just to cut off and join some of the windows that contain the same and taking away the silent components. Then some segments are joined and then they are considered. In the meanwhile, the oxygen saturation is also detected, and also the similar pre-processing is done to it. And then if the drop in the oxygen saturation is more than, in this case, 2%, then the sound segment is retained for classification. So in this case, this means that essentially if there is a doubt that the sound segment might be sleep apnea, and that's is where the oxygen saturation is highlighting this, then the classification of the sound is necessary. And the sounds are classified by a system that considers various features. One is the duration of the breathing sounds. One is the energy spectrum. The log of the energy, as we saw, was very indicative. If it's the duration also highlights if it's a snoring signal and if it's simple noise. This is done with these features. When the features are calculated over the sounds, then this is all fed into a framework that classifies if a combination of these, if you have a breathing, a certain duration, if you had some snoring, if you had some noise, if your energy spectrum of that breathing is of certain kind, then there's a threshold, and all of this is useful to understand if the episode was normal or apneic. Because I do like to highlight how well the systems are generally doing. I only have a couple of slides on this. So on the x-axis there's a time domain signal there, and the various little dots are indicative of how the system has classified the various frames. So you can see there that a snoring point is highlighted, breathing, and snoring. The red sign is when the snoring is not being detected appropriately by the system. And in fact, you can see it in the spectrogram there that perhaps the deeper red here should have highlighted that this is a snoring episode, and this was missed for some reason by the system. So the feature of the energy and the duration are not able to detect this appropriately. However, we'll talk more about sleep in the next set of lectures, but this is a graph that shows how the system results correlate, considering the index. This index is calculated by using the classification system that we have, and is compared with the results of the PSG. So PSG is polysomnography, is the status quo for detection of sleeping episodes and sleep apnea, in fact. But we'll see in one of the slides is a system that puts you in a bed with lots of wires and lots of EEG, and it's very difficult to sleep with that, but it's a gold standard for doing that. But this system that just considers audio is very correlated. The picture is very correlated. So this is the system and the index calculated by using the data that we have. So only SpO2 and audio, and this is the system with polysomnography and lots of other information. And the two systems are very correlated. So here we have a scalable, simple system that is able to do what another quite difficult system is able to do. So I've given you some examples and some features of how audio can be used for detection of various aspects related to health in general. We've seen some wheezing, some breathing, and some sleep apnea examples. And I will stop here, and on the next lecture, we'll continue with some more audio examples. Thank you.